Good morning everyone. Today we are going to start what is called as transient heat conduction. Let's write transient heat conduction, or we can even call this transient heat conduction as unsteady heat conduction. Now today's plan of lecture is that today we shall try to cover what is called as lumped system analysis. Before this, we shall try to see what is that we can, why study transient heat conduction. So that we will cover initially, and then try to cover lumped system analysis and the criterion of the lumped system analysis. That is, we are going to introduce a number called Biot number. Okay. So if time permits, we shall get started with plane wall heat transfer. Okay, that's the overall plan for today's lecture. So first, next question is why study time dependent heat conduction? Time dependent heat conduction. If you recall heat diffusion equation, del squared T by del x squared plus del squared T by del y squared plus del squared T divided by del z squared plus q dot triple prime, that is the heat generation term, divided by the thermal conductivity is equal to 1 by alpha dou T by dou T. Okay. So this is the temperature variation along the x direction, this is the temperature variation along the y direction, this is the temperature variation term along the z direction, and this takes care of the unsteady term. And so far in the previous chapters we have neglected this term because we considered steady. So temperature essentially is a function of x, y, z and t in real life case. There are very many examples. If you just take a body and put that heated body into water, or you have just started heating, just take your tawa and you have put on your gas stove and your tawa is getting heated up. So the temperature variation of the tawa, in all of these cases the temperature is a function not only of space but also of time. So before we take up space, what we shall try to do is we shall take up only the temperature variation with this time, but the temperature of the body being uniform, that is, it is not dependent on space. So now if I take copper ball, and let us say this is having high thermal conductivity and this is having 70 degrees Celsius, 70 degrees Celsius, 70 degrees Celsius, 70 degrees Celsius, 70 degrees Celsius. The thermal conductivity of copper is roughly around 400 watt per meter Kelvin. So you can see that here the temperature within the body is uniform. That is, it does not vary, everywhere it is uniform. That is, its form is same everywhere, uniform. So it is same everywhere. But now let us take a potato, and in the potato I had kept this potato in a cooker and after it has boiled I have taken this potato out. Now this potato, if I measure the temperatures at various locations, at one location it can be 60, another location it is 65 degrees Celsius, in center let us say it is 75 degrees Celsius, it is 75 degrees Celsius, and here 70 degrees Celsius. So here it is 60 degrees Celsius. So here the temperature is not uniform. This body where the temperature is uniform can be called as, or can be thought of as, a body is lumped. You can think of it as a copper ball as a lump, because it is all sitting at the same temperature. So this body, a lumped body, is that body where the temperature is uniform. That means temperature is only function of time but not space. So it is uniform with space. So that's the lumped body definition. So we are going to take up next what is called as lumped system analysis. Lumped system analysis. So as a starting off, let me take a hot metal and put this hot metal into a fluid. That is, you have a container which is filled with water. Okay. Now I have taken a hot metal which is sitting at Ti, that is, at a time t equal to 0, the temperature is initial temperature Ti. Now I drop this into liquid. Now this body temperature is going to vary with time, that is, temperature is going to vary with time. Question is, how do I get this temperature distribution? Now the fluid temperature which is there, it is sitting at T infinity, that is, T infinity is fluid temperature. Fluid temperature. Now the question is to get this temperature distribution using lumped body analysis. That is, I am assuming that within the body there is no variation of the temperature, it is same everywhere. So for doing that, I need to take the recourse of energy balance equation. Energy balance equation. So what is that? Is E dot in minus E dot out plus E dot G is equal to E dot St. E dot St. Now what's happening? I have taken that the body is hot, that means Ti is definitely greater than T infinity. That means the heat is going to get transferred from the body to the liquid but not reverse. So that means E dot in is 0, because body will only lose the heat and there is no energy generation. I have not put any heater or any chemical reaction is occurring inside. So energy generation term is also 0. So you have minus E dot out is equal to E dot St. Okay. So now how does the body lose its heat to the fluid? One of the ways in which it will lose its heat to the fluid is by convection. It can actually occur through radiation also, but we are neglecting radiation and taking only the convection. If that is the case, then I can use Newton's law of cooling, that is minus HAS into T of T minus T of T minus T infinity is equal to E dot St, which we have written earlier, rho Vcp into dt by dt. Let us write each term. What are these terms? H is heat transfer coefficient between the fluid and the body, heat transfer coefficient. As is the surface area of the body. If it is a sphere, 4 pi r cube. Surface area or the bathing area, and rho V is the volume of the body, and rho is the density of the body material, density of the body material, and Cp is specific heat of the body material. So we have told everything here. So now what we will do is we will define what is called as theta for the sake of maths. Theta equal to T of t minus T infinity. Now what will happen to this is minus HAS theta, that is this equation I am writing, HAS theta equal to rho V Cp. If you differentiate this from this, d theta by dt is equal to dt by dt. T infinity is constant. So because T infinity is constant, so dt infinity by dt is not going to exist. So we can replace dt by dt as d theta by dt. Now if I rearrange this, so I can write this as rho Vcp divided by HAS into d theta by theta is equal to minus of dt. Okay. So all these are taken constant, so I can integrate between the limits, that is I have started from time t equal to 0. At any instant time t I want the temperature distribution, that is T. Now I am starting from theta I. What is theta I? Theta I is Ti minus T infinity, that is initial. Theta I to theta, where theta is defined here. So this is what I get. Now what can I do is, if I integrate this another thing what I will do is, this rho Vcp HAS I will call this as tau. Why I will call, a little while from now I will explain that. Tau of, if you integrate this, you get log of theta between the limits theta I to theta is equal to minus t minus 0. Okay. So what will happen is, if I take it forward, rho Vcp divided by HAS integral of d theta by theta, theta I to theta is equal to 0 to t dt. So this is tau of log of theta, theta I to theta is equal to, this is minus sign, so minus t. So log of theta minus log of theta I, log of theta minus log of theta I equal to minus t by tau. This I can write log of theta by theta I equal to minus t by tau, and theta by theta I is equal to e to the power of minus t by tau. Now let us, that is t of t minus t infinity divided by Ti minus t infinity is equal to e to the power of minus t by tau. I have achieved what we started off, that is the temperature distribution as a function of time. Remember, this is for lumped body and I have done lumped system analysis. Now what is this tau? Let us try to understand. Tau actually is called as time constant. So if you take tau is equal to rho VCP divided by HAS. So if you take the unit of rho kg per meter cube, volume is meter cube, Cp is joule per kg Kelvin, and H is watt per meter squared Kelvin, and surface area is meter squared. So this is meter squared. So kg gets cancelled, meter cube gets cancelled, Kelvin gets cancelled, meter squared gets cancelled, watt is nothing but joule per second, so joule gets cancelled. So I end up getting the unit of tau as seconds. So that is why it is called as time constant. So that is the significance of this. Another way of looking tau is tau equal to 1 by HAS into rho VCP. So that is 1 by HAS can be thought of as resistance, thermal resistance, and rho VCP can be thought of as thermal capacitance. That is RT is thermal or convective resistance to convective heat transfer, and CT is thermal capacitance, or it is a kind of inertia, thermal inertia. In fact, instead of capacitance, if you are comfortable, you can think this as thermal inertia. The body is having inertia to undergo the heat transfer. Now if I were to plot this, if you see this temperature distribution, the y axis is the theta, that is T minus T infinity upon Ti minus T infinity, and this is time, the x axis is time. Now the x axis, so if you just see, this is how exponentially the temperature is dropping. Okay. So these different curves are for different time constants. So that is this, the first one will have lowest time constant and the top one will have highest time constant. That is this, the first one, the lowest time constant one will respond fast to the with the time, the temperature changes with the time faster than the first one where the time constant is quite high. Okay. So that is about the temperature distribution. Now let us take up the energy that is generated within the time t. That is, if you take what is the heat transfer rate, that is Q equal to HAS into T of t minus T infinity. Okay. So now I want the total energy which is generated between the time 0 to t. So this is actually Q dot, because that is watts, this is joule per second. So I am looking for joules. What is the energy? What is the energy or the heat transfer which is accumulated over time t? So that is Q dot dt 0 to time t. So that is, if I put this HAS T of t minus T infinity dt 0 to t. Now T minus T infinity we had defined, if you recall, T of t minus T infinity, I have defined this as theta. So I will replace this HAS, I can pull that out, HAS I can pull out of the integral because they are constant and they are not dependent on time. That means I have considered that H is constant. Okay. So, I can write this as theta dt between the limits 0 to t. If you recall, we just derived theta equal to theta I into e to the power of minus t by tau, minus t by tau. So, you can get q equal to h a s integral of theta I e to the power of minus t by tau dt 0 to t. So, theta I is constant, so I can pull that out, h a s theta I. If I integrate this, I write this as minus t by tau divided by minus 1 by tau between the limits 0 to t. So, q equal to minus h a s theta I into tau into e to the power of minus t by tau minus e to the power of minus 0. Okay. So, that is minus h a s theta I, tau is nothing but rho v c p divided by h a s into e to the power of minus t by tau minus 1. This is q. So, q equal to, so what you get is q equal to h a s theta I, h a s, sorry, h a s, sorry, this h a s, this h a s, this h a s gets cancelled out. So, you end up getting rho v c p theta I into, if I subsume that negative sign into the bracket, I get 1 minus e to the power of minus t by tau, 1 minus e to the power of t by tau. So, this is in joules the energy accumulated over time 0 to t. And just let me recall what is theta I. Theta I is nothing but Ti minus T infinity. Ti is temperature at T equal to 0. That just a reminder. Okay. So, this we now got the summary of this lumped body analysis is we got the temperature distribution, that is theta by theta I equal to theta by theta I equal to e to the power of minus t by tau. Theta is T of t minus T infinity divided by T of I minus T infinity. So, this is the temperature distribution we got, and at the same time we got the how much is the heat transferred between the time 0 to t. So, both these temperature distribution and the heat transfer we have gotten. Now, the question is, next question what we have to address is, what is the criterion, what is the criterion for a body to be told or to be considered as lumped, to be considered as lumped. That is the next question. To address this, we introduce a number called, Biot number, criteria for lumped system analysis. So, for the criteria of lumped system analysis, we introduce what is called Biot number. Biot number equal to HLC by K. So, H is the heat transfer coefficient, LC is volume by surface area. Okay. So, if I consider a solid body, within this solid body there is conduction taking place, but at the same time there is convection at the surface, convection is taking place at the surface. So, the Biot number can be thought of as, if you just take this, if I rewrite this, H delta T divided by K by LC into delta T. That is, this is the convection, this is nothing but the heat transfer rate, that is convection at the surface, of the body divided by conduction within the body, conduction within the body, because this is the Fourier's law of conduction and this is the Newton's law of cooling. Okay, heat flux, that is heat flux. So now Biot number can also be thought of as, I can rewrite this, if I push this up, LC by K, that is and divided by 1 by H. So I can consider this as conductive resistance or conduction resistance, that is resistance for the conduction to take place within the body, conduction resistance within the body divided by convective resistance at the surface of the body, So if the conductive resistance, for the body to be lumped, Biot number ideally has to be 0. That means there should be no conductive resistance. There should be nil conductive resistance. Conductive resistance is 0. When can that be happening? When conductive resistance can happen when K is tending to infinity, that is infinite thermal conductivity. If you have, there is no resistance for conduction, then the temperature is uniform everywhere. But practically it is considered that Biot number less than or equal to 0.1 is considered as lumped body. So here we stop about this lumped body, and we will take up this lumped body analysis in the next class in much more detail, and also we will solve a problem on lumped system analysis in the next class. Thank you.